Hello everyone, I'm Dr. Rao. I hope you guys are doing well. Welcome to my YouTube channel Mathematics by Dr. N. Rao. Today I am going to deal with very interesting topic of basics of the numerical methods. Okay, so exact number, approximate number, errors, okay, and significant figures, etc. So, guys, before going to this beautiful fundamental or this beautiful part of the basics, I request each and everyone to subscribe my YouTube channel, like and share the videos among your classmates, among your colleagues, okay, and comment in the comment box also, and press the bell icon to get the further notification. So guys, we will start with the word exact and approximate numbers. First of first of all, I will love to introduce exact and approximate numbers. Okay. So, as we know, in the number system, there are two types of number involved to represent the complete mechanic of the number system. There are number one, it is exact, and second type approximate number. Approximate number. Okay. So there are two kinds of number. Remember this point. Two kinds of number: exact numbers and approximate number. Exact and approximate numbers, for example, 1, 2, 3, and square root 2, pi, e, etc. Okay. Written in this manner, approximate number are those numbers which represent the number to a certain degree of accuracy. To a certain degree of accuracy. So if we see these numbers, so these are exact numbers. Okay, these are exact numbers, and these are also exact numbers. Remember this point, exact numbers, because these numbers are also parts of our universe, and whatever in the universe exists is exact in its nature, right? But can we exactly define this number? No. We can define exactly these numbers, okay? These numbers are exactly defined, okay? Exactly defined, okay? Exact, these numbers are exact in its nature and exactly defined. But on the other hand, these are also exact in its nature but not exactly defined. But not exactly defined. So we are talking about these number, not exactly defined. This category of the number will decide the approximate values. Okay. And as I have told you, the approximate numbers are those numbers which represent the numbers to a certain degree of accuracy. For example, the approximate value of pi is 3.1416, and another approximate value I am going to write of the pi here, 3.1416 or you can write 5. Okay, 5 9 2 6 5. It is another approximate value, and this value of pi, this value of pi is better than this value of pi. Okay, so it is a better approximate value of pi. Okay, but you cannot write the exact value of pi. Okay, that's why these types of number, square root 2, pi, e, this type of irrational numbers are exact in its nature, but are not exactly defined. So you required to compute their a better approximate value. Okay. Okay. I hope you guys understood this point. Now we talk about significant figures, okay, or significant digits. Now, what about the significant digits or significant numbers? Okay, so the digits that are used to express a number are called significant digits or significant figures. I'm writing here the digits that are used to express a number is called significant digits or significant figures or significant figures. For example, the numbers 3.1416, okay, and 0.66667, right, and 0.406 40687, and you can take another number if you required. Okay, so the numbers contains 5 significant digits to represent these. Okay, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5. So these number contains the 5 significant digits to express the number. Okay, come on. On the other hand, if we talk about 0 point 0.00023, right, so it contains the 2 significant digits to express this number. Okay, since the zeros serve only to fix the position of the decimal points. Okay, these zeros plays role in to fix the position of the number in the decimal points only. But this, okay, here you can see this 0 is not involving here to fix the position of this number, because this number is start with the non-zero digits here. Okay, it contribute in the other way, not in terms of the position of the decimal, but these zeros are involving in this number to fix the position of the number in terms of decimal. Okay, so that's why here the 2 significant digits are 2. Okay, and in these 3 cases the significant digits are 5. So similarly, the numbers, if we talk about 0.00145, okay, and 0.0000145, all of these numbers has two significant digits, three significant digits only, 1, 4, 5, okay, because these zeros plays the role only to decide the decimal position of this number, okay. That's why here three significant digits are involved, so it is very easy to decide the significant digits, okay. Now on the other hand, if we talk about 25 600, if we talk about this number, so the number of significant figures is uncertain, okay. The number of significant figures is uncertain, whereas the number 2.56 into 10 to the power 4 or 2.560 into 10 to the power 4 and 2.5600 into 10 to the power 4, okay, have 3, 4 and 5 significant digits. There are 3 significant digits for the same number, remember this point, and it has the 4 significant digits, okay, and it has the 5 significant digits, okay, because just if zeros comes just after the decimal, then it decides the position of the decimal in the number, but these zeros are coming after the non-zero numbers of the decimal, okay, non-zero digits of the decimal. So in such types of number, the significant figures or significant digits are uncertain, okay. So in numerical computation, we come across which have large number of digits, and it will be necessary to cut them to a usable number of figures, and this process is called rounding off, okay. So you will you will face the very big number, very big approximate numbers in your computation, but in this case you will face some issues, okay, to use these big values, okay. So for your computation you require uh, to restrict this number up to the shortest digits, okay. So how will you restrict these numbers up to the shortest digits? It means you require to rounding of these numbers, okay. So I am again repeating, in numerical computation we come across numbers which have large number of digits, and it will be necessary to cut them to a usable number of figures, and this process is called rounding off, and this process is called rounding off, okay, and this process is called rounding off. It is also important point, okay, rounding off. So it is usual to round off number according to the following rule. There are some rules, okay, according to the following rule. So to round off a number to n significant digits, okay, discard all digits to the right of the nth digits. For example, you are there are some numbers 1 2 3 4 5 7 1 6 9 2 3 and so on. This number is going to up to infinity, and you need to round off it up to the 5 decimal places here, 5 decimal places. Okay, and similarly I have the another number 1 0.1 4 5 6 7. Okay, and then 3 or you can write here 4. Okay, 3 5 6 and 7. You need to round off this number also up to the 5 digits. Okay, up to the 5 digits. Okay, and on the other hand, you have another number like 1 4 5 6 7. Okay, 6 7 and 6 7 and 8 5 and so on, and you need to round off these numbers, this number up to the 5 digits, up to the 5 digits here, rounding off. So what is the process to round off such types of number? There are some rules. What is the rule? Less than half a unit. Okay, to round off a number to n significant digits, n significant digits. For example, we need to round off this number up to the 5 significant digits, 5. Okay, then discards all numbers to the right of the nth digits. Okay, then discard all these numbers. Okay, discards all these numbers, cut all these numbers in the first process. Okay, and if this discarded number is number 1, if this discarded number is less than half a unit in the nth place, less than half, less than half, less than half means if we talk about less than half, what does it mean? 0.5, right? If it is less than 0.5, if it is less than 5, okay, then the nth digit unaltered, then the nth digits unaltered, okay, means the rounding of number for this is to 0.141564. Okay, I am again repeating. If on discarding the number up to the nth place, up to the nth digits, for example, we are rounding off this number up to the 5 digits. So if nth digits means this digit, right, is less than half, so you can say it is 4, and it is less than 0.5. Okay, so then the number will be unaltered. Okay, unaltered, there is no change into up to the 5 digits, no change. Okay, on the other hand, if it is greater than half a unit in the nth place, if it is greater than, like this, if it is greater than half a unit, so it is greater than half a unit, obviously it is greater than 5.5, it is greater than 5. Okay, half a unit. So then the nth place increases by unity. Okay, then the rounding of number for this number will be 1 4 5 6 8. Okay, this one, and in case exactly half a unit in the nth place, so this case, okay, so it is exactly half a unit in the nth place, so increase the nth digits by unity if it is odd. Now see, it is odd. Okay, then exactly half a unit in the nth place, then increase the nth digits by it, by if it is odd, otherwise leave it unchanged. Okay, otherwise leave it unchanged. So obviously if it is exactly half of the unit, okay, then you need to see this, okay, if it is odd or even, then you need to if it is odd, then leave it as it is, okay, then leave it as it is, and leave it unaltered if it is even, okay. So guys, one more thing, the numbers that rounding off is said to be correct to n significant figures, okay. I'm writing here, we generally use in our questions this statement, okay, the number thus round off is said to be correct to n significant figures. N significant figures, correct to n significant figures, okay. And we have used this statement in our argument of the questions. Find the roots of this polynomial correct to 3 decimal places, correct to 4 decimal places, correct to 5 decimal places. So it is the case, okay. Now for example, the numbers given I'm writing here are rounding off to 4 significant figures. For example, 1.6583, okay. I need to round off this number correct to 4 decimal places or correct to 4 significant figure. So it will be written as 1 2 3 4. So 1 2 3, now 4. So 4 is 8 and it is greater than, now 8 the fourth place it is 8 and it is greater than 5. So in case if it is greater than 5, okay, then so you need to check the fourth place, okay, you need to round off this up to the fourth place. So you need to check this number, okay. First we will write 1.658, then what about 3? It is less than half or greater than half, okay. If it is less than half, then leave it as unchanged, okay, there is no change. Now in case of for example 30.0567, so correct to 4 decimal places we need to see this number, okay. So we need to round off this number to 4 significant figures. So you can write 30, okay. So 4 significant figures, these will be decided from here, yes, exactly 30, this one, okay, and it is exactly half of the number, and this one is the even place, so it will be 30.06. These are 4 significant figures to represent this number. And in the another number like 0.859378, okay, 4 significant figures, you can write it as 0.859. Now what about 3? Because see 3, right? So if it is, we need to see this place. Okay, we need to cut off it here, so we need to see this place. If it is greater than half of the unit, then 1 will be added in the last digit, otherwise leave it as it is. Okay, similarly, if we talk about 3.14159 to 4 significant figures, so you can write 1, 3.14 and 2. Okay, we will see this and we will see this. So it was total about the rounding of the numbers. Okay, exact numbers and approximate numbers, significant figures of the numbers. Similarly, we will talk about errors. Now we talk about the errors. Okay, so first type of the errors we talk about absolute error. Absolute error, right? And I am going to write the simple definition of the error here. Error, okay? Error is what? How will you define the error? So it is a numerical difference. It has a single line definition. It is a numerical difference. Remember this point. It is a numerical difference. Numerical difference between exact number, between true value and its approximate value. You can say like between true value and its approximate value right? It is a numerical difference between true value and its approximate value. Okay, now in case of absolute error, how we will define the absolute error? So if capital X and if capital X, okay, capital X denotes the true value, if capital X denotes the true value, okay, and x1 denotes its approximate value, then absolute error is denoted by, these are very simple definition, is denoted by E means error, A means absolute, is denoted by EA and is defined as EA is equals to x minus x1, modulus of that. Remember, modulus of x minus x1. Mod stands for the numerical difference and mod stands for the positivity of the errors. Okay, what is the difference in between x means true value and its approximate value? It should be considered positive always. That's why we are using here modulus sign. Okay, what does it mean? It means that either it will be x minus x1 in case if true value is greater than its approximate value. Okay, or you can find the difference x1 minus x in case if x1 is greater value means approximate value is greater value than the true value. So you can compute this to make the positivity of this. So combinedly we write modulus x minus x1. Okay, so it is the absolute error. Now we talk about the relative error. It is very simple. Okay, relative error. So how will decide the relative error? It is denoted by E A, it ER, right? ER, and is defined as these are very simple definitions, okay, and is defined as ER is equals to EA absolute error and then divided by its true value, okay, relative error. Now we talk about percentage error, okay, percentage error. So it is denoted by EP and is defined as EP is equals to relative error multiplied by 100. Okay, relative error multiplied by 100%. So it is the percentage error, and it is very simple to perform these errors corresponding to some values of true value and its approximate value. Now we will learn these three errors, and we will understand these three errors with a very simple example. Okay, so what is the example here? I am writing a example here. If 0.30, 0.33 and 0.34, okay, are three approximate value, values of 1 by 3, right? Then find which one is the best approximation. Which one is the best approximate value? So the work is very simple to decide here. Another solution. Come on. First of all, I am going to write the true value x, that is what, 1 by 3. Then I am going to write the three approximate value, that is x1 is 0.30, okay, x2 is 0.34 and x3 is 0.33, right? So these are three approximate value of x, true value x. So first of all, I am going to calculate here absolute error due to the approximate value x1 equals to 0.30. Okay, so it is very simple to calculate. Simply in the modulus part you write x minus x1, that is 1 by 3 minus 0.3. okay, so what about this computation? It will be 1 by 3 minus 3 by 10. okay, so you can simply say, you can take LCM 30 and you can write here 10 minus 9, so you will get 1 by 30. So it is your absolute error, 1 by 30. okay, due to you can write here dash, okay, due to 0.30. Similarly, you can find the absolute error due to the second approximate value, that is 0.33, and it will be decided as 1 by 3 minus 0.33. Then you can write it as 1 by 3 minus 33 by 100. Okay, so simply you can calculate it as 300, right? 300 and 100 minus 99. So you will get 1 by 300. Okay, so it is the second error. Okay, now what about the error number third? Absolute error third, due to the approximate value x3, that is 0.34, and you can compute it as 1 by 3 minus 0.34. okay, that is what 1 by 3 minus 34 by 100. okay, and you can take LCM here 300, and you can take the modulus also. So 100 minus 102. So you will get minus, and due to this modulus it will be written as plus 2 upon 300, right? So 1 upon 150. So you have got three errors due to the three approximate value. Error number 1, right? Error number 2, error number 3. Obviously, if you see here, error number 2 is the smallest error. Is the smallest error for these three value. Okay, so this if this error is the smallest, then it is the best approximate value, or it is the best approximate value. So to decide the best approximate value, you can just simply compute the errors due to these three approximate values, and in the parallel, similarly you can compute their corresponding relative errors also. So relative error will be decided by EA decided by X, right? EA X. Okay, similarly for this value, relative error will be decided by EA double X divided by true value. Similarly for that, ER, so you can indicate also them double dash, triple dash. Okay, so double dash divided by capital X, and the computation is very simple. X we have calculated 1 by 30, and the true value is 1 by 3. Okay, so you can write it as 3 by 30. Okay, so you can say 1 by 10. So it is the relative error 1 by 10. Similarly, here you can write 1 upon 300 and 1 upon 3. So you can decide 3 by 300 or 1 by 100 is the relative error. And same here, 1 by 150 and 1 by 3. So you can write 3 by 150, right? And you can write 1 upon 50. These are three relative errors due to three approximate value. And parallelly, you can decide their percentage error. Okay, so EP1, it will be due to relative error 1, okay, multiply by 100%. Similarly, EP percentage error will be decided by ER second double dash multiply by 100%. Okay, these are very simple to compute. Okay, EP triple dash ER triple dash multiply by 100%. Come on, these are very simple. Okay, so ER is 1 by 10 multiply by 100%. So it is what 10% error here. Okay, in the first value. In the second value, you write here 1 upon 100 multiply by 100%. So there is a 1% error. Okay, and in the last value, that is what 1 by 50, and then multiply by 100%. So you can write here 2%. So in the last value, the 2% error is required here. So guys, the computations and the errors, types of the errors and analysis of the errors is very easy. So keep in touch, and thanks for the watching the video. So see you in the next video lecture with awesome content.